Okay, so we've been going through the different gas laws relating the different variables of volume, temperature, pressure, and number of moles, and we are now up to Dalton's law of partial pressures, which basically says that the sum of all the components of a gas mixture is equal to the total pressure of the mixture. So each gas, it doesn't matter what the gas is individually, a mixture of two gases, the amount of pressure each one exerts is going to solely be dependent upon how much of each gas there is, and the sum of their pressures will give us the total pressure. So this is a very simple formula. You can see here the total pressure would be equal to the pressure of gas A plus the pressure of gas B plus the pressure of gas C, etc. If there were two gases, there'd just be 2. If there were 8 gases, it would be, the partial pressure of all 8. And again, this would really just be determined by how much of each gas there is. So let's take a look at a sample problem. Very, very simple. So we have a mixture of hydrogen and helium. Technically, it would be H2. And the total pressure is 1.33 kPa, kilopascals. If the partial pressure of the hydrogen is 0.45 kPa, what is the partial pressure of the helium? So the way you would write this, P total is going to be equal to the pressure of the hydrogen plus the pressure of the helium. Does it matter that it's hydrogen or helium? No. Because remember, individual gas particles are so spread apart that it really doesn't matter if it's a large molecule, if it's a tiny atom, it doesn't matter because there's huge amounts of space between the particles. So the total is just going to be equal to those. Now we can manipulate this formula since we are looking for the helium. We could subtract from both sides the hydrogen and it would look like this. So the total pressure minus the pressure of the hydrogen would give us the pressure of the helium. And so now it's just a matter of plugging in our numbers. So it's going to be 1.33 kPa minus 0.45 kPa, and that is going to give us 0.88 kPa. Now, in this case, for sig figs, just a reminder, it's been a long time since we've done them with addition and subtraction, but it's actually not based on the number of significant digits, it's based on the number of decimal places. And so both of these go to the hundredths place, so your answer would also go to the hundredths place. Don't make the mistake of using our multiplication rule and think we have to round it to 2 sig figs because this has 2 and this has 3. For addition subtraction, it's the number of decimal places. They both go to the same decimal place, so that makes it very, very simple. Now, there is another type that you could see of Dalton's law of partial pressures, and that's this type. So if the pressure outside is 760 millimeters of mercury and 21% of the gas in the atmosphere is oxygen, what is the partial pressure of the oxygen? And so in a problem like this, again, the percentage of the total, basically, if it's this percent oxygen, then this percent of the pressure is coming from oxygen. So we are going to convert our fraction to a decimal, 0.21 times 760 millimeters of mercury. And this will give us a partial pressure. It's basically calculating 21% of the total pressure because 21% of the total pressure is going to come from the oxygen. And when you work this out, you're going to get 160 millimeters of mercury. So this would be another type of pressure, partial pressure problem where they could give you the percentages of the gases. And again, the percent of the atmosphere or of the gas in the container, then that's the percent of the pressure that it will contribute. Okay, and that brings us to the ideal gas law. So the ideal gas law is a little bit different. How are you going to know that it's going to be the ideal gas law? Because you'll notice that nothing's going to change. We don't have a P1 and a P2, a V1 and a V2. In this case, this is going to combine the relationships between all of the gases, and it basically says that the pressure times the volume will be equal to the number of moles times a gas constant called R times the temperature. The temperature does need to be in Kelvin. Also, our volume needs to be in liters. If they were to give you, say, milliliters or cubic meters or some other unit of volume, you would need to convert your volume to liters for this. Now, your pressure can actually be in atmospheres or kPa, kilopascals. Those are the only two pressures that'll work for this formula, at least based on the gas constants that we're providing you. So there are two gas constants. They're really the same. If the pressure is given to you in atmospheres, you're going to use this one, 0.0821 atmosphere liters per mole Kelvin, which looks really complicated, but I'm going to show you in a second how all these units are going to cancel when you plug this in. If they gave you kilopascals, kPa, as the pressure, then that's when you're going to use the 8.314 kilopascals liters over moles K. So you do not need to memorize the gas constant. You just would need to know which one to pick. And again, it's really, really easy. Look at the pressure that they give you and then determine whether it's ATM or kPa. If they were to give you a pressure in something else, like millimeters of mercury, torr, something like that, you would need to convert it to either atmospheres or kilopascals to use this formula. All right, so how many moles of gas at 100 degrees Celsius does it take to fill a 1 liter flask at a pressure of 1.5 atmospheres? So first thing, we're going to need to convert our temperature to Kelvin. So notice, first of all, they're asking for moles, and nothing is changing. We're not being given something and then the conditions change, like a temperature 1 and a temperature 2, or a volume 1 and a volume 2. We're being given a temperature, so here's our temperature. And we're going to need to add 273 to that. So this is going to be 373 Kelvin. So we have a T. A 1 liter flask. So we have a V. And then our pressure is a P. All right. So our formula, PV equals nRT. And in this case, we're looking for N. So we can manipulate this. If we divide both sides by RT, we would get that N would be equal to PV over RT. All right, so let's go ahead and plug in our numbers. So our pressure is 1.5 ATM. Our volume is 1.0 liter. Which R are we going to use? Well, our pressure is in atmosphere, so we're going to use our 0.0821. Now notice this is ATM liters over moles Kelvin times our temperature, which was 373 Kelvin. Now, I'm going to change my color of marker here just to show you. Notice all of our units are going to cancel. Atmospheres cancels, liters cancels, Kelvin cancels because it's on the bottom of this and compared to here. And our answer will be in moles. So we know we have this set up right because all of our units are going to cancel. So when you plug all of that in, you are going to get an answer of 0.0490 moles. For our significant digits, you would look at all of your numbers and round to the least number of significant digits. So in this case, that's going to be 2 significant digits. I don't know why I have 3 there, actually. Let's see, this has 1.5, this is 2 significant digits, this is 2 significant digits, this technically has 3. So actually, I would have rounded this, I wouldn't have included this 0. It would be 0.49, 2 significant digits. Remember, the zeros in the front are not significant, but these two are. And you would not use your gas constant R to determine significant digits. You would look at all the numbers they provided you. So the temperature, the volume, and the pressure. Those are all measurements, and then round based on the least number. So again, that would be 2 significant digits, not 3 for this answer. Okay, one more. So the other thing that can happen with these is that you could be given grams. Oh no, so now we have to convert to moles first. So this is the only problem in the whole chapter where you might have to do a conversion. So what is the volume? So we're looking for a volume. STP, that's standard temperature and pressure. So that's going to be 273 Kelvin is going to be our temperature. And our pressure, we'll use 1 atm. These are, you're not using sig figs for these, because these are given to you. They're not measurements that you're taking in a lab. So technically our only measurement in a lab is going to be this one. So we're going to have 3 sig figs, just an FYI, in our answer. Okay, so we are looking for a volume. All right, so we're going to be using PV equals nRT. All right, so we have a P, that's 1 atmosphere. We have a V is what we're looking for. N, we don't actually have, but we can get it. So we have 9.45 grams of C2H2. We now have to convert that to moles. So 1 mole of C2H2, and this is where you have to go to the periodic table. So you may remember that carbon weighs 12, so 2 carbons would be 24 grams. And then hydrogen weighs 1, and there's 2 of those, so add 2. So this should weigh 26 grams C2H2. So we are converting from grams to moles, so this will give us N. I'll come back to that. So we have PVN. R is our gas constant, so it's 0.0821. That's ATM. Liters over mole Kelvin. So PVNR, and we had a T of 273 Kelvin. All right, so let me grab my calculator. So we're going to convert our, so 9.45 divided by 26, and I get 0.363 moles. So now we have our N. Okay, so we're solving for volume. So if I manipulate my formula, volume is going to be equal to nRT over P, right? All right, so let's go ahead and plug in our numbers. So N was 0.363 moles, R 0.0821, and that's ATM liter over mole Kelvin. T, I'm running out of space, is 273. That would have been on top. I apologize for this being messy. And then we divide by our pressure, which is 1 atm. That makes it really easy. So we're just going to be dividing by 1. Notice our units. So moles will cancel with moles. This is Kelvin will cancel with Kelvin. Atmosphere will cancel with atmosphere. And our answer should be in liters, which makes sense. So 0.363 times 0.0821 times 273, and I get it 8.14, because we have 3 significant digits in our answer. Liters should be our correct volume. So that's how you would calculate this one. So the only extra step is that you had to convert to moles from grams. Okay, last slide. Yay! So, deviations. So the gas laws and the ideal gas law are based under ideal conditions. So when is it that real gases don't behave according to these laws? There are really 2 conditions: high pressure and low temperature. So let's talk about why. So if the pressure is very high, that means that the gas particles are getting crunched together, like you're forcing them into a tiny space. Now remember, one of the rules about gases is that the size of the particles doesn't matter. But it is going to matter when they're under high pressure. So they're not going to obey the gas laws properly. And then low temperatures. If you lower the temperature, they're going to move so slow, they're going to start to become a liquid. So it's best at lower pressures and higher